need to look at is how big the key space is. All right. There's a theorem. It's handy. There are C sub R minus 1 ways to insert parentheses into a string of R elements. And C sub R minus 1 or C sub N is what's called a Catalan number. So this is, once again, the story of graduate school. You go down these rabbit holes that you don't expect, and one of my rabbit holes was, let's play with Catalan numbers, because we need to insert parentheses, and that tells us how many ways to do it. There's a handy dandy formula for Catalan numbers. There it is, with lots of factorials and chooses. You can do it that way. And remember that we also have this one more thing. We've got this element, the secret element that we throw onto the end of the key. So the size of the key space, if my messages are broken up into blocks of size n, that means I have n minus 1 multiplications. So there are C sub n minus 1 ways to do that. And then we've got this extra element C at the end. And C comes from the quasi-group, so you've got the cardinality or the size of the quasi-group, the number of ways to choose your value of C. So we have C sub n minus 1 times Q. That's the size of the key space for this particular message authentication code with blocks of size n. This is old, so I didn't update this. I didn't look now as to what the acceptable size for a key space is. This is, I don't want to tell you how long I've been out of grad school. This is 15 years old, so it's probably not up to date, but the acceptable size for a key space used to be 2 to the 128th elements. It turns out that C sub 68 and C sub 69 bracket that. You don't really need your blocks to be 68 or 69 characters long, because you've also, once again, got this extra multiplier for the secret element that we are using to replace innermost multiplications. But these would be a minimum for block sizes 15 years ago. Not sure what it is today. All right, how about security? So even theoretical cryptographers have to talk about security. Yeah, in general, security is really, really hard to talk about for new crypto systems and new message authentication codes and new hash functions, because the way you talk about security is by putting it out there and letting people attack it, and then either saying, oh, okay, that attack doesn't work, I'm good to go, or crud, that attack does work. How am I going to tweak my protocol to prevent against this attack? And I, when I did this, was a graduate student at Iowa State University, and nobody really cares about my PhD dissertation besides me, who got to graduate with a PhD and teach at WLC. So there are not really very many attacks about this. I don't know. It's hard to talk about security. If I really wanted to publish this, I would need to throw it out there and say, break this for me, please, and see if I could fix it. That's the answer. One small attack that my advisor came up with, and this is where that secret element comes in. We know that the quasi-group needs to be highly non-associative, right? We talked about that already, highly non-associative. Where's this constant coming from? Where's this constant coming from? Why did I throw that in there? It seems like it just adds weirdness and makes it more complicated. It does increase your key space, but that's not the reason that I added it. It is because if you don't put the constant in there, there's an attack. And it's not a attack that will probably let Eve forge authentication tags for any meaningful messages. So it's not necessarily an adaptive attack, but there is an attack that exists. And once again, any attack that exists is problematic. So here's the idea, the attack that this inserted secret element guards against. Let's assume that Eve gets a message and an authentication tag. I'm calling the authentication tag Z, right? So this is what we're assuming when we're talking about attacks against this. And then what Eve is going to do is look at pairs of elements that circle to the same thing. They multiply out to the same thing. So we've got different pairs of elements, but the result of the multiplication in the quasi group is the same. And then she can find these innermost products. She's going to look for these innermost products that are the same if she gets another authentication tag that matches. Because what she's done is she said, okay, let's say, for example, I've got a message where I have 2 circle 5 as an innermost product. And then there's a whole bunch of other stuff going on here, but 2 circle 5 is an innermost product, and let's say that's equal to 3. Let's say she also plays with this and discovers that 4 circle 6 is also equal to 3. So she can replace this innermost product 2 circle 5 with 4 circle 6. What she's discovered is the hash of this message and the hash of this message are the same. So h sub k of m1 is equal to h sub k of m2. And therefore, she's able to forge an authentication tag. She can figure out where innermost products are by looking at which authentication tags match. That's the issue with this. So by adding another secret piece of information into these innermost products, she can't come up with where these innermost products are, and therefore she can't forge message authentication codes, because instead of 4 circle 6, instead of that, we've got 4 circle C, circle 6, and she doesn't know what that secret key C is. So there's an additional piece of information that helps her from finding where these innermost products are. That's the reason that this secret element from the quasi group got added. Otherwise, she can find these innermost products basically by guess and check. There's a way to do it by guess and check. Does that kind of make sense? It's deeper than that, and it's a whole chapter in my dissertation. So this is the quick 2 to 3 minute version of where that's coming from. But that basically, that secret key serves to hide the innermost products. That's basically what's going on here. Hides the innermost multiplications. So, okay. Anything for questions up to this point? One more thing then. Size, 2 more things. Size or necessary quasi-group properties has to be large, has to be highly non-associative, has to be easy to represent, and circle needs to be easy to compute, because you need ease of computation for message authentication codes. So large and highly non-associative. Highly non-associative should beg the question, what exactly does that mean? Yeah, I don't know. Played with that a little bit in my dissertation as well. That was kind of the last chapter add-on, and didn't necessarily come up with a great area. So every research talk should end with areas for future research. These are some of them. How secure is it? What other attacks can Eve try? What does highly non-associative mean? How do we even measure this? How can we say how non-associative is a quasi-group? And then here's the kicker. How do we create large, highly non-associative quasi-groups? I can just throw numbers at a board on a Latin square and make a quasi-group. That's not a problem. But is it highly non-associative? Is it going to have the properties that I need? That's what I'm looking for. So areas for future research. If anyone ever looks at my dissertation and says, I'd like to play with this a little bit more, there they are. I have no expectations that anyone will, but that's the areas for future research that exist. So, okay, there is my research in 42 minutes or less. You are seeing 5 years of grad school in this presentation. Not really, but that's the basic idea. Questions that people have? John, yeah.
This might have been said or at least implied, but so with the fact that your key is how you arrange parentheses around a message,
Yep.
the message needs to be a certain length to have any semblance of security, right?
Yes. So what we will do is block the message and then pad it at the end if necessary. Yeah.
Okay.
Other questions? Does it make sense? Yes-ish. That was a very quick overview, super quick. And if I were doing this in class, I could gauge your facial reactions and see if it makes sense. And I can only get some of them in this case. So, yes.
Oh, cool idea.
So, all right. Thank you for letting me share my research with you. It's fun. I like talking about it every now and again. And it's an interesting practical application from, again, not a super practical. I would need to pair up with somebody to actually get this implemented. And how are you going to store a quasi group? And it's not a table lookup. Like, that's just stupid. There's no way to do multiplication with a table lookup. So how are you going to compute all of these things? And there's a lot of practical issues that I simply do not deal with, but other ones do. So, all right, going once, going twice. Anything else for other questions? All right, I got to look at my schedule because there's 2 topics left and I don't remember which one I did first. I think on Wednesday we're doing secret sharing schemes. I'm pretty sure. I think that Wednesday is secret sharing schemes, Wednesday and Friday. And then next week, Monday and Wednesday are poker over the phone. So we were talking about poker over the phone. Those might be inverted, but those are the 2 topics that we have left. All right, anything? All good? Cool. All right, I'll see you on Wednesday. Thanks, guys.